Have you ever stopped and thought about just how fast AI is evolving? It's kind of mind-blowing. We're talking large language models with billions, even trillions of parameters. These things are growing faster than even Moore's law predicted. But there's a catch. All that intelligence needs serious computing power,
Right, yeah.
which translates to mountains of expensive hardware.
You're absolutely right. Building and running the infrastructure for these AI behemoths, it's not just a tech challenge anymore. It's an economic one, too. It's become this race to create bigger and better models. But the rising cost, that's creating a real barrier, for researchers and smaller companies.
So for today's deep dive, we're going to be taking a look at how to build a super powerful AI system without needing a blank check.
Right.
Our source. A research paper by a team at DeepSeek AI in Beijing.
The paper is called Fireflyer AI-HPC, a cost-effective software hardware co-designed for deep learning. What makes this one fascinating is that it comes from people who actually built a massive system, offering real-world solutions and insights into how to balance performance with a budget.
That's what I love about these deep dives, getting into the practical side of things.
Yeah.
The paper, it starts by laying out the challenge. AI models are getting so huge, they need thousands of GPUs to train. And those GPUs, especially the top-of-the-line ones, they get pretty pricey.
And here's where the problem gets even trickier. AI's demand for power, it's growing tenfold every year. But hardware improvements, those are only happening at about 3 times every T2 years.
Oh, wow.
It's like we're on this treadmill that's constantly speeding up.
Sounds exhausting.
Yeah.
What does that kind of pressure mean for a small team of researchers trying to make a breakthrough?
It puts them in a real bind. Do you pour your limited funding into buying more and more powerful hardware, knowing you'll be stuck with these huge energy bills? Or do you scale back your ambitions, work with smaller models, and risk being left behind by the labs with deeper pockets?
So what did this DeepSeek team do differently?
Well, they built a system called Fireflyer 2, which is kind of the underdog champion of AI supercomputing. They managed to achieve nearly the same performance as systems built with, the most expensive components.
Right.
But at a significantly lower cost.
Okay, but 10,000 GPUs? That's mind-boggling. It's not like you just plug them into a wall socket and hit go.
Right.
What kind of architectural magic did they pull off?
It's all about smart design, squeezing maximum performance out of every component. Think of it this way. Each node in their system has 8 of those A100 GPUs.
Okay.
They're powerful, but not the most expensive kind. They're the PCIe type, not the super pricey SXM kind.
Yeah.
And they connect them all with a single super fast InfiniBand network card. They even planned ahead, leaving space for upgrades down the line, which is clever when you're working at this scale.
So they're being strategic with their hardware choices. But even with all those GPUs, you need a way to connect them and make sure that data flows smoothly. What did they use for that?
They went with a 2-layer fat tree network, which is a pretty common design for high-performance computing. Imagine an upside-down tree, where the leaves are individual compute nodes, and as you move up the branches, they connect to larger and larger switches until you reach the trunk with the highest bandwidth.
Ah, so the fat part means it has a lot of bandwidth at the top to handle all that data traffic.
Exactly.
Did this save them money compared to other systems?
Absolutely. A 2-layer fat tree is less expensive than the 3-layer setups you find in, some supercomputers. But here's the kicker. They compared Fireflyer 2 to the industry standard, the NVIDIA DGX A100, which is built with top-of-the-line, super expensive components.
Okay, drum roll, please. How did it stack up?
Fireflyer 2 achieved about 83% of the DGX A100's performance, but at about 60% of the cost and using 40% less energy.
Whoa! That's a serious win, especially for researchers or startups working with tighter budgets. So they're saving money on the GPUs in the network. Are we sensing a theme here?
Definitely. But remember, hardware is only part of the story. You also need software that can orchestrate this whole symphony of GPUs, managing the data flow and making sure everything runs smoothly.
Right. It's not like you can just hit play and let 10,000 GPUs do their own thing.
Exactly. It's like conducting an orchestra. Even a small misstep can throw off the entire performance. DeepSeek had to come up with some clever parallelism strategies to divide the work efficiently across all those GPUs.
So what did they do on the software side? Did they just use off-the-shelf tools, or did they get creative?
They definitely got creative. They developed 2 key software innovations that really set Fireflyer 2 apart. The first is called H-Reduce. It's a custom communication library designed to overcome some of the limitations of using PCIe GPUs.
Hold on, you're telling me they use software to work around hardware limitations? That's impressive.
It is. PCIe GPUs aren't as fast at communicating with each other as the more expensive SXM type. So H-reduce essentially bypasses those bottlenecks, making data transfer much faster and more efficient.
So they're being strategic with their software, just like they were with the hardware. What was the second innovation they developed?
The second is called Hayscale. It's a framework that optimizes popular training techniques for their hardware.
Okay.
It's like a toolbox for squeezing even more performance out of their system.
So they're not just working around limitations, they're actively finding ways to get more out of what they have. I like their style. Can you give us an example of how this Hayscale thing works?
Sure. They used it to optimize a technique called fully sharded data parallel, which involves distributing data and model parameters across multiple GPUs to speed up training. Think of it like this. Instead of one chef trying to prepare a huge feast, you have a team of chefs, each working on different parts of the meal simultaneously.
Ah, so they're breaking the work into smaller chunks and tackling it in parallel. Makes sense. Did they see any real improvements using this approach?
They did. Their optimized version of fully sharded data parallel cut training time almost in half compared to the standard PyTorch implementation.
Wow. So they're saving time and money. It's all starting to add up. But with a system this complex, they must have also put a lot of thought into making sure it's stable and reliable, right?
Absolutely.
Yeah.
Reliability is crucial with these massive systems. Imagine training a complex AI model for months only to have a hardware glitch wipe out all that progress.
Yeah.
It'd be devastating.
Okay, so how did they build in that stability and prevent those kind of catastrophic failures?
They took a multifaceted approach, including developing specific tools to manage their massive system. They created a checkpoint manager to regularly save progress during training. It's like having a super fast save button for your AI models. And it's incredibly efficient thanks to their custom 3FS file system. They can write huge amounts of data in seconds, minimizing any losses from crashes.
That's reassuring to know. They have backups. But even with backups, you'd want to catch potential problems before they cause a crash.
Right. Exactly. Think of it like a routine checkup for your supercomputer. They developed a tool called Validator, which regularly tests the hardware to catch those potential issues before they turn into major problems.
So they're running tests, saving their progress, anything else they're doing to keep things stable.
Well, this is where it gets really interesting. They're not just trying to, prevent failures. They're also embracing failure as a learning opportunity. They dedicated a whole section of their paper to analyzing the different types of hardware failures they experienced over a year of running Firefly or 2.
Now that's what I call a deep dive. So they weren't afraid to talk about what went wrong.
Not at all.
Yeah.
They meticulously tracked every hiccup, every crash, every glitch. They broke them down by category. Software errors, hardware errors, network errors. It's like a taxonomy of AI supercomputer failures.
So they're turning their failures into a roadmap for future success.
Exactly. By analyzing that data, they were able to identify patterns and develop strategies to prevent similar failures from happening again. And even better, they shared their findings in the paper, providing valuable lessons for the entire AI community.
That's a great example of collaboration in action. So what were some of the most common problems they encountered? Give us the juicy details.
One thing that surprised them was the high rate of NVLink errors. Now, NVLink is a technology that connects multiple GPUs together for faster communication. It's like a high-speed data highway between them.
Okay. So they're using this NVLink to speed things up. What went wrong?
Well, it turns out that the NVLink bridge connectors, which are used to physically connect the GPUs, they had a higher failure rate than expected.
Huh.
It's a reminder that even the most cutting-edge technology has its limitations.
So even when you're building with the best parts, things can still go wrong. Makes you appreciate the importance of redundancy and backup plans.
Absolutely. Another issue they faced was network flash cuts, sudden disruptions in communication between the nodes.
Yeah.
And imagine your internet suddenly going out in the middle of an important video call, but on a much larger scale.
Ouch. I can relate to that feeling. But I bet the fix is a little more complicated than resetting your router when it's happening to a supercomputer.
Definitely. These flash cuts could be caused by various things. Faulty hardware, software bugs, you name it.
Right.
Pinpointing the root cause could be a real challenge.
So what's their strategy for dealing with these network hiccups?
They used a few strategies. One was to design their network to be as robust as possible, like a highway with multiple lanes and alternate routes. to minimize the impact of any disruptions.
Okay, so they're building in resilience from the ground up. What else?
They also implemented things like traffic shaping and congestion control mechanisms to prevent any one part of the network from getting overloaded. Imagine having, like, traffic cops for data, directing the flow to keep things moving smoothly.
I love that analogy. But even with all these precautions, I'm guessing there were still times when things went sideways.
Of course. And in those cases, having a quick and efficient recovery plan was essential. Remember their checkpoint manager. That saved the day more than once by allowing them to restore progress from a saved point in time.
It's like a time machine for their AI models. Speaking of models, let's shift gears and talk about the software side of things. We've covered the hardware challenges and how they built instability, but we haven't gotten into the details of their custom software yet.
You're right. The software is like the brains of the operation, telling those thousands of GPUs what to do and how to work together.
And DeepSeek didn't just use off-the-shelf software. They created their own tools and libraries to optimize their system. One that stands out is HRFreduce, a communication library designed specifically for their PCIe architecture.
Right. HRFreduce was key to achieving that high performance at a lower cost. Remember how they use PCIe GPUs instead of the more expensive SXM GPUs?
Yeah.
Well, PCIe GPUs have some limitations in terms of how quickly they can communicate with each other.
Right. So HRFreduce helped them overcome those limitations.
Exactly. It bypassed some of the bottlenecks in the hardware,
Okay.
making data transfer much faster and more efficient. They basically outsmarted the hardware limitations using clever software.
I'm starting to see a pattern here. They're not just throwing money at the problem, they're finding ingenious ways to get the most out of their setup.
You got it. And HRFreduce wasn't their only software innovation. They also developed a framework called HeyScale, which is designed to optimize popular training techniques for their hardware.
Okay. It sounds like HeyScale is this powerful toolbox for maximizing the efficiency of their system.
That's a great way to put it. And it includes like a whole suite of tools and techniques, including optimized versions of those parallelism strategies we talked about earlier. Remember, those strategies involve dividing the work across all those GPUs to speed things up.
Right, like dividing a huge task into smaller, more manageable chunks. What kind of results did they see using HeyScale?
One example is their optimization of fully sharded data parallel, which distributes data and model parameters across multiple GPUs to speed up training. Okay. Their version cut training time almost in half compared to the standard implementation.
Wow. It's amazing how much of a difference clever software can make. So they're saving money on hardware, optimizing their software. Did they mention anything about what's next for them?
They did. In their paper, they outlined their vision for the next generation of PCIe architecture. And it's clear they have ambitious plans to push the boundaries even further.
Okay, I'm hooked. What are they focusing on?
They're specifically targeting MOE models. That stands for a mixture of experts. They're a type of AI model that's becoming increasingly popular for large language models.
Wait, mixture of experts. I think I heard of that. Refresh my memory. What are those again?
Imagine a team of specialists, each with their own area of expertise, working together on a complex problem. That's essentially what a MOE model is. It's made up of multiple smaller models or experts that each specialize in different tasks.
Ah, right. It's like having a team of specialized AI working in consult. So these MOE models are powerful, but probably require a lot of computing power.
Right, exactly. And that's why DeepSeek AI is designing their next generation system with MOE models in mind. They're planning to have a 1-to-1 ratio of GPUs to network cards on each node, similar to what NVIDIA is doing with their high-end DGX H100 systems.
So they're taking inspiration from the best in the business, but I thought they were all about being cost-effective. Won't all those extra network cards get expensive?
That's where their ingenuity comes in. To keep costs down while maintaining performance, they're considering implementing a multi-plane network, which is like building a multi-level highway system for data, with different lanes for different types of traffic.
I'm picturing data zooming around at different levels of a superhighway. But seriously, a multi-plane network, that sounds pretty complex.
It is. But they're also looking into using row C switches instead of IB switches, which can significantly lower network costs. They're constantly searching for that sweet spot between performance and affordability.
It's like they're the ultimate bargain hunters for AI supercomputing. It's inspiring to see what they've been able to accomplish by thinking outside the box.
It really is. DeepSeek AI's work is a testament to the power of innovation and a reminder that even with limited resources, you can achieve remarkable things with, a bit of creativity and a lot of hard work.
So they've optimized their hardware, created ingenious software, and now they're already planning their next generation architecture. What else did they cover in this paper?
Well, there's one more important aspect we haven't discussed yet.
Okay.
The intricate details of their networking and storage systems.
Okay. Let's dive into that. What can you tell us about how they manage the flow of data within this massive system?
One of the most fascinating aspects is how they tackled the challenge of congestion within their fat tree network. Remember, even with a lot of bandwidth, traffic jams can still happen if you're not careful.
Right. It's like rush hour on a highway. Even with multiple lanes, things can back up if too many cars try to go through the same bottleneck. So how did they prevent their supercomputer from turning into, like, a digital traffic jam?
They used a combination of clever techniques. First, they were really strategic about how they connected their storage servers to the compute nodes. Imagine spreading out the on-ramps and off-ramps on a highway to prevent bottlenecks.
Okay.
That's essentially what they did with their data traffic.
Okay, so they're distributing the traffic evenly. What else?
They also made some adjustments to the way their custom communication library, hrefreduce, interacts with the network. They optimized the data paths to avoid the busiest parts of the network, kind of like finding alternate routes to bypass rush hour traffic.
That's clever. It sounds like they squeezed every bit of efficiency out of their network design. Did they mention anything else about their networking setup?
There's one detail that really impressed me. They combined the network for the compute nodes with the network for the storage servers. This is called a computation storage integrated network. And it's pretty unusual. Most supercomputers keep those networks separate.
So they merged two highways into one superhighway. That seems like it would make congestion worse, not better.
You'd think so. But they use a technique called traffic isolation to prevent different types of traffic from interfering with each other. It's like having dedicated lanes for different types of vehicles. They also prioritize traffic using different service levels to ensure the most critical data always had a clear path.
It's amazing how much thought goes into designing these systems. Okay, let's talk storage. They mentioned a system called 3FS, a high-throughput distributed file system they developed themselves. What's the deal with 3FS?
3FS is designed to handle the massive amounts of data that, AI models generate. They use super fast NVMe SSDs for storage. And they optimize the system to take full advantage of their speed. They even added a feature to prevent congestion when multiple nodes try to access the storage simultaneously.
So they've thought about speed, efficiency, and stability at every level. But with all this focus on hardware and software, what about the human side of things? Did they mention anything about making Fireflyer 2 user-friendly for researchers?
They did. They actually developed a platform called HAI Platform to make it easier for researchers to use Fireflyer 2.
Okay.
It handles things like scheduling tasks, allocating resources, and even dealing with fault tolerance.
So it's like an operating system designed specifically for a supercomputer.
That's a great analogy. HAI Platform, it streamlines a lot of those complexities, allowing researchers to focus on what they do best, developing and training AI models.
It sounds like DeepSeek AI has created this complete ecosystem for AI research. It's impressive how they've addressed every aspect of building and using a powerful yet cost-effective supercomputer.
It really is inspiring. Their work shows that you don't need, unlimited resources to push the boundaries of AI. By combining smart engineering, innovative software, and meticulous attention to detail, they've shown what's possible when you challenge the status quo.
I think that's a great takeaway for our listeners. Innovation can come from anywhere, and sometimes the most groundbreaking ideas come from those who are resourceful and determined to find a better way.
Absolutely. And with the cost of AI constantly rising, it's exciting to see teams like DeepSeek AI paving the way for more accessible and affordable AI research. Who knows what incredible discoveries and applications this new generation of supercomputers will enable.
It's definitely an exciting time to be following the world of AI. And that wraps up our deep dive into DeepSeek AI's remarkable Fireflyer 2 supercomputer. We hope you learned something new today. Thanks for joining us on the Deep Dive.